Over a century has passed since physicists first broke down the structure of the universe. Scientists have discovered an engine that is based on the mathematics of probability lying dormant beneath the surface of normal, everyday reality. Everything is presented as a possibility in this interpretation of quantum physics, which is known in a roundabout way as the Copenhagen interpretation. This continues until something is presented as a fact. But in all seriousness, what exactly does that imply? Despite decades of research and philosophical musings, the gap between the unresolved features of a quantum system and the measurements that can be seen by everyone with their own eyes has hardly shrunk. Despite all of the talk about collapsing waveforms, cats in boxes, and observer effects, we are no closer to understanding the nature of reality now than early physicists were in the late 1920s. Despite this, there are scientists who are of the opinion that the gap in understanding that exists between quantum physics and Einstein's well-known general theory of relativity may in fact contain vital clues. In the previous calendar year, a team of researchers from the University of Chicago hypothesized that the mere proximity of the black hole could cause a mass that is currently existing in a haze of quantum states to be pulled towards a singular fate. They have presented a new forecast in the form of a preprint before it is sent out for peer review, and this time they have discussed their thoughts on a number of horizons. Imagine something minute and tangible emerging from the shadows contained within a closed box. It is a haze of possibilities, but they are not visible. There are no specifics that can be determined regarding its position, rotation, or velocity. Additionally, there is no limit to the range of intensities that are possible for the light that it emits. This composition throws with potential, much like a wave that seems like it could continue on and on forever. This spectrum of possibilities can be compared to itself in the same way that a wave on the surface of a pond can split up and come back together to create a recognizable pattern of interference. The potential of the ripple, however, is reduced when it comes into contact with other ripples and becomes entangled with them. Decoherence is the term that physicists use to refer to both the process by which this interference pattern changes and the results that it produces. Three renowned physicists, Dagny Danielson, Gautam Satish Chandran, and Robert Wald, investigated this process in the context of a thought experiment that could lead to an intriguing contradiction. Any researcher who peers inside the box in an effort to find the particles light will, in the process of doing so, entangle themselves and their surroundings with the waves that are being concealed by the particle. This will result in some degree of decoherence. What would happen, however, if another person was observing the scene from behind and saw the light emitted by the particle with their own eyes? They could accomplish the same thing with the wave of the particle by becoming entangled with the light that it emits, which would further limit the possibilities of the wave's outcomes. What if the second observer was located on a planet that was several light years away, and they were using a telescope to look at the box? This is where things start to get strange. Even if it took years for the electromagnetic waves of light to travel from the box to the second observer, the two observers would still become entangled. According to quantum theory, this will also lead to a discernible shift in the particle's wave, which the first observer will notice well before their colleague on a faraway world even begins to set up their telescope. This is because the first observer will have access to more information than the second observer. What if, on the other hand, the location of the second observer was inside a black hole? Even if light from the box could easily pass beyond its horizon and plunge into the abyss of warped space-time, information about its destination with the second observer would not be able to escape due to the special and general relativity that governs the universe. Either our understanding of quantum mechanics is fundamentally flawed, or general relativity has some serious issues that need to be fixed. Both of these possibilities need to be investigated further. Or, if you believe Danielson, Satish Chandran, and Walt, our second observer is irrelevant to the discussion. The event horizon is a point beyond which nothing can escape. It serves as an observer and, in the end, is what causes everything to lose its coherence. As if a horde of enormous eyes were scattered across the sky, watching the entirety of the cosmos come to life. Are you terrified yet? The worst possible outcome occurs. It's possible that other phenomena besides black holes could also turn space-time into a one-way motorway. Every object traveling close enough to the speed of light will, at some point, reach a horizon from which the information it emits can never, ever possibly return. This will happen at some point in the future. According to the findings of the most recent study carried out by the three, round horizons have the potential to bring about an analogous loss of coherence in quantum states. It does not imply that the universe possesses a brain or anything like that. Instead, it is possible that the findings will make it possible for objective theories to be developed regarding the resolution of quantum states into absolute measurements and possibly the point at which quantum physics and gravity converge. At least for the time being, there is still something wrong with the way the universe operates.